Morning, AJ. I thought you were taking the AP Lit test.
No, I not put myself through that.
Oh, interesting. Because all your classmates were sure that that's what you were doing. Were they being facetious or
Maybe I
just
should have just
wrong?
gone and acted like I was doing it then.
Okay, so it's just Teresa and Finley.
Wait, Teresa's an AP Lit? Why is she AP Lit?
Because there's no AP Lit.
Oh, really? That's weird. Did not enough kids sign up or something?
Oh, no, it switches every year.
Oh.
You know what I would like to do, and this is on a related topic. I would love to get rid of AP Calculus and just teach calculus. I really would. I know everybody wants the credit, the college credit, and I agree that the college credit is a good thing. The problem thing I don't like about teaching AP Calculus is the time crunch. California schools start at the beginning of August. They take the AP test the same time we do, which means they have almost an extra month to learn calculus. And when we're actually doing AP Calculus properly, we spend a month and a half doing nothing but practice AP problems. Well, you're not learning calculus if you're just spending a month and a half doing practice problems. You're learning how to do AP test problems, which isn't bad. I mean, they're good problems or good questions. I just think how much more we could do if we didn't have that time crunch of we have to be done by this day in April. And then we got 2 months left, and what do? Well, we still learn calculus in a normal class. We still do some stuff. But I don't know, it's forced and artificial. And I would love it. I mean, well, it'll never happen because people want AP. And like, the college credit is nice, but I think it would just be really nice to be able to say, hey, you know what? We're all going to learn calculus this year. But there it is. Guys, I want to talk about related rates. I gave you the intro yesterday. For those of you who came in late, I went home early yesterday because I thought I had nothing left to do. And I was like, oh, what the heck, I'm out of here. And then I came in this morning and realized I'd never made the videos for 5.6 related rates. So I'm going to teach you related rates. I'm going to make videos this afternoon. Everything you need to know is in that title. Rates, things changing with time. This is, I mean, you can probably, off the top of your head, think of a dozen different examples of where things change with time and you might be interested in what's going on. We're going to look at a really cool problem down the road called the lifeguard problem. And the idea is you're a lifeguard, you're standing on a beach and you see someone drowning. Well, you got two things that you're going to have to do. Thing one, you're going to have to run along the beach. And thing two, you're going to have to swim. But you do those at different speeds. So how far should you run before you dive in the water? You swim slower than you run, so you could theoretically dive in the water right here and swim out at an angle. That maximizes the amount of swimming you have to do at a slower speed. Or you could run all the way down the beach to where you're right in front of the person drowning and then swim out. Or is there a place where you could run partway down the beach and then swim out at less of an angle to minimize the amount of time that it takes to get to the drowning person? It turns out dogs do this instinctually. You guys ever gone to a beach or a lake with a dog and thrown a ball out in the water? Any of you had dogs that do that, like retriever dogs? Dogs will run along the beach and then jump in the water and swim out, and they instinctually minimize the time it takes. If you watch, somebody actually did a study. They noticed their dog doing this. They noticed their dog running part way and then swimming, as opposed to running to here and swimming, or just swimming from here. And I wrote a book called Dogs Do Calculus, or something like that. I've got it at home. It's an awesome book because he just started testing. He just started doing trial after trial after trial where he'd throw the ball, mark where the dog went into the water, and then went back and did all the calculations. And it turned out the dog basically optimized the situation every time.
How did the dog like know that?
Well, that's beyond the scope of the book. he just pointed out they do it. He's like, look, I proved they do it. I have no idea how they do it, or it's weird. So anyway, things that change with time, and then related. That I think is self-evident. 2 different or 3 different quantities, multiple quantities that change together. And I gave you the example of filling up the balloon yesterday. The radius and the volume are both changing at the exact same time. But they're changing in a way that you can predict. You have an equation that relates them. And therefore, if you know how one is changing, you can predict how the other is changing. And that's the whole point of related rates. So generally what we've got is we've got multiple functions of time. So we have multiple functions of time. And we might say x of t and y of t. Both x value changes with time, y value changes with time. By the way, we probably won't get to it, but this is the idea of parametric equations. Parametric equations are a strategy whereby you can change linear or nonlinear motion into 2 variables changing with time. Instead of input x, output y, you input time and you output x and y. And you'll see it again at some point. If it's necessary, you'll see it again. So what we've got here is we've got some particle motion. We've got some particle moving along a line, and we know that that particle has coordinates x and y, and we know that both x and y are changing. And so we're counting time instead of counting x and counting y. We count time, and then we say, oh, where's the particle? So here's a basic strategy and this is just to illustrate how this process might work. What if I wanted to know where that particle was relative to the origin? Now, of course, we know that we could draw a right triangle and that this is some x value and this is some y value, which means that the distance that the particle is from the origin is the square root of x squared plus y squared. Pythagorean theorem. But all 3 of these are changing with time. So if the question then became, how fast is the particle moving away from the origin, we would take the derivative with respect to time. The rate of change of the distance from the origin with respect to time, in other words, how fast is that particle moving away from the origin, is equal to. Now, let's take the derivative of this with respect to time. Well, chain rule, outer function, square root. Times inner function. Well, keep in mind that both of these are functions of time, and I am taking the derivative with respect to time, which means that the chain rule says that the derivative of some function of x with respect to time is the derivative of the function times the derivative of x. Okay? We all cool with that? This is your straight up basic, this is how the chain rule works. That is some function of whatever, how you're taking the derivative. So this becomes 2x times the x dt. This becomes 2y dy dt. And there's the derivative with respect to time of the distance of the particle from the origin. This really is the tricky, this is tricky. We run into the issue just of how do I know when I'm supposed to do the derivative this way? It's just a function of getting used to the chain rule and how it works. And remember, it's outer, work your way in. Now, the trick here is that we're taking the derivative with respect to something else. We were always saying derivative with respect to x. So if I was saying, how does that distance change with x, I would have a slightly different problem. I would still have the outer, but my inner would be, well, the derivative of x squared with respect to x is just 2x. I don't have to worry about that. And the derivative of y with respect to x, oh, look, there's that chain rule. And the only difference between what we're doing here and what we're doing here is that in the past, we've always said, let's take the derivative with respect to x. Let's find out how y changes as we change x. Well, how does y change as we change x when we're dealing with the x squared part? We don't care. It's not changing. There is no y to think about. So we only had to do the chain rule on the y portion of the derivative.
I was always confused why we only did it on y.
Well, if you really, really wanted to do all the extra writing, you would do this.
Yeah, this makes a lot more sense.
Well, what's that?
This one.
So we don't write it.
That
Yeah.
makes a lot more sense.
Yeah, the chain rule says you always have to take the derivative of the thing inside. But if the thing is inside is, remember that the derivative of x is just 1. So we just say, okay, and we ignore it. It's sort of like, I don't know if you guys remember working with your friends who weren't great at math, is that 2n divided by 6, I divide both sides by 2, and then I write 1n is equal to 3. And I've actually had students say, okay, well, what do you do next? And well, now I need to divide both sides by 1. And then they'll write n is equal to 3. And it's like, they don't recognize that that's meaningless. It doesn't tell you anything. But I've literally had students do that because their brains don't process the math like ours do. They just don't get it. They're like, well, there's a number in front of there, so I've got to do something with the number.
At least I understand the process.
Mostly they've memorized the process, but they have no idea what it means.
Oh.
And there's the difference. The difference between people who are good at math and people who aren't is that people who aren't good at math can memorize a process given a problem. If I see multiplied, then I need to divide. It's sort of the reason that people write that as a squared plus b squared. They've memorized that if you've got a 2 on the outside of parentheses, you distribute. And therefore, those are the same thing. But they don't understand the difference between two kinds of problems. They just know, oh, I've got this thing. If I see a number on the outside, I distribute the number. Oh, good. Then that's a squared plus b squared. And the funny thing is that no matter how many times I go back to them and I say, hey, a plus b times a plus b, draw a generic rectangle. And they draw the generic rectangle. They write a squared plus 2ab plus b squared. And then on this, I've had kids do this on the same page, 3 questions down, do the same problem and write it as a squared plus b squared because it just doesn't process. They're not understanding what it means. So anyway, here we go. We've now figured out how fast this particle is moving towards or away from the origin. Now, what do we need to know in order to figure that out? Well, we need to know where the particle is because it's going to be different here than it is there. We need to know how fast it's changing in the x direction, and we need to know how fast it's changing in the y direction, which means that there are actually 1, 2, 3, 4, 5 pieces of data now, and we need 4 of them in order to solve this problem. We need to know position and we need to know rate of change for both directions in order to determine how fast something is moving away. So, I'm going to switch the order of my examples because I want to do an example that does one of these distance problems. So let's look at an example. And here's the classic example. Hot air balloon. And it's rising. And you've got some observer standing over here. And here's the situation. The angle that the observer is watching the balloon is at pi over 4 radians. It is changing at a rate of 0.14 radians per minute. And this is something that's easily measured with a fairly simple instrument, a clinometer, and easy enough to do that rate of change. And what we're told is that we want to know how fast the balloon is going up. And I feel like we're missing, are we missing one thing here? Oh yes, and the observer is standing 500 feet from the spot where the balloon launched. So what we have to do now is we just have to relate all the various different things and say, okay, what can we figure out? Well, that sure looks like an X. We know that's a Y. What do we know? We know X is 500. We know theta is pi over 4. We know d theta dt is 0.14. We don't know Y, and we don't know dy dt. But we also know that this is the thing we're interested in, which means we need a relationship x, y, theta. Well, we have a relationship between x, y, and theta, agreed? It's tangent. We know that tangent of theta is equal to opposite over adjacent, which means that the length of that side is equal to x times the tangent of theta. We also know, and I'm going to color code, that that's a constant. And that these are changing. Which means we don't have to worry about the rate of change of x with respect to time. Which means that we can write our equation as y equals 500 times the tangent of theta. And I want to know how fast that is changing. It's time to do a derivative. The derivative of y with respect to time equals 500. Constant multiplier rule says I can just set the 500 there and never think about it again. Times a derivative of tangent. Anyone remember that one? Secant squared times chain rule the rate of change of the angle. I'm done except for the calculations. I know that theta is pi over 4. And I know that the rate of change of the angle with respect to time is 0.14. Secant is 1 over what?
Fine. No cos. Wait.
Sine, no cosine. Guys, remember how to remember?
It's the opposite.
It's always the opposite of the one you think it is.
Yeah.
You'd think secant and sine should go together because cosecant and cosine should go together. And because you think that, it's wrong. They're backwards. So this is 1 over cosine. All right. So I'm going to rate this as 500 times 0.14. And I'm going to do all the math in my head. I'm going to assume that calculator isn't readily available as I'm standing out in the field watching the balloon. Over cosine squared pi over 4. Do we know cosine of pi over 4? Of course we do, because we're awesome at the unit circle. Pi over 4 is the middle one, right? It goes 1 over 1 over 2, 2 over 2, 3 over 2. Small, medium, large, agreed? They're all over 2, and this is 1, 2, 3. Which means I don't really have to memorize anything. I just know it's all 1, 2, 3, and everything's over 2. And if you really want to be tricky, oh look, it's root 1, 2, 3. And pi over 4 is the middle one. So this is root 2 over 2 squared. 500 times 0.14, what's the easy way to do that?
Calculator?
Why not multiply it by 1,000 and then split it in half? What's 1,000 times 0.14?
140.
140. Well, what's half of 140?
70. What? Oh, yeah.
Right? Guys, you ever wonder how people do mental math? Really good mental math? Well, thing one, they're super smart.
Yeah.
I'm super smart. I can do mental math. Hey, guess what you all have going for you? You got the super smart part. So then it's just a matter of learning the tricks. Guys, that's a trick.
Yeah.
People who don't know how to do mental math will be like, oh, well, it's 5 times 0.14 and 5 times 0.1 is 0.5. And or maybe they're going 500 times 0.14 and trying to get, no, 500 is half of 1,000. 1,000 is moved the decimal 3 places, and then half of that's 70. Boom, you're done. Root 2 over 2 squared. Agreed? Root 2 over 2 squared is 2 over 4, but it's divided by, so I can flip it over. Means I get 140. Can you believe that we just multiplied 500 times the secant of pi over 4 squared times 0.14 without ever touching a calculator?
No, I couldn't.
But guys, it wasn't hard. The only reason it took as long as we did is because I had to explain all the steps I was doing in my head to you. As you do it more, you get better at it, and then you don't have to waste your time digging out a calculator. You just say, wait, I know that one. Now, maybe you get one that you don't know. Maybe you get a weirdly complicated one. Probably are. You're going to get a weirdly complicated one. But this is a problem that you might see on an AP calculus test that doesn't allow a calculator. The non-calculator portion. And what's the answer? The answer is 140. Non-calculator portion, because there's nothing on there we couldn't do in our heads with a little bit of thinking.
I like how the 0.14 just like directly correlates the answer.
Coincidence? I don't know. Yeah, probably. I mean, combination of 500 and root 2 over 2 more than anything else, because that could have been virtually any number, and that would have been exactly the same, because these things cancel each other out, as it turns out. Last step. Notice that I wrote the units on there because I have come up with a number, but I have not answered the question. Somebody asked me how fast the balloon was rising, and the correct answer is, at that moment in time, the balloon is rising at 140 feet per second. That answer is not valid unless we're at pi over 4. Change that angle, that whole thing changes. So the last step of every one of these related rates problems needs to be interpret the answer at that moment in time. You could say when the angle of elevation is pi over 4 radians, the balloon is rising at 140 feet per second. Or you could say at that moment, because it means the same thing. The problem you were given was the moment when the angle of elevation was pi over 4. But it's really important that you interpret this. And guys, this is a real life thing. Your boss is going to send down some complicated math problem because he's got a degree in business administration and you're the math person. And he's going to say, solve this for me. If you send him an email that says 140, wait, what? 140 what? He didn't even understand the problem, really. He was just like, oh my gosh, there's this complicated problem, figure it out for me. If you send him back an email that says 140, I'll do that. I'll make fun of my students sometimes. They'll say 140, and I'll say 140 what? Cows per square foot? And they're looking at me like, cows per square foot, what? Feet per second, and that's big.
That'd be inhumane.
Could be. I mean, it'd be stacked on top of each other.
That's humane.
So let's talk about process, and then we'll do some more examples.
I don't think one cow would fit in a square foot. You
Yeah,
have to you have to like stick it on his butt and squeeze it as small. They'd just be soft.
The thing you have to remember is if you are going to make an example to make a point, it has to be a ridiculous example. Otherwise, they might think, oh yeah, that seems reasonable.
Really good point.
Because that will be the follow-up question. Mr. Ermening, it doesn't make sense to have a number of cows per square foot for a variety of reasons. And you just say, yeah, okay. But you didn't tell me what it was, so I don't know. I'm just guessing. Guys, let's talk about strategy. Steps. Guys, remember close reading in English? There's a reason they teach close reading. No. Contrary to popular opinion, teachers don't do anything for the specific purpose of boring their students. Thing one, bored students aren't nearly as fun to teach. But a lot of the stuff that you learn, this is a fun conversation I've had with students. It's like, oh, well, there's no point in doing this. And I think to myself, okay, you're 14 years old. You have no idea what the point of anything is at this point in your life. You don't understand anything because you don't know anything. So you could assume at age 14 or 15 that the whole point of school is torment you, and I get it. It seems like torture. But everything that we teach generally, unless you've got one of the worst teachers in the world who's just trying to get through the day, everything we teach you has a purpose. Why do I need to learn to explicate poetry? Why do I need to close read? Am I ever going to when am I ever going to need to explicate poetry, Mr. Armerding? Never. But the skills involved will stand you in good stead down the road. Why do we teach close reading? Because close reading is how you get relevant information and how you understand what is being asked. How many times have you sat in a math group in algebra or geometry or even algebra 2, and you sat around and the people in your group said, I don't get what the question is. And maybe you didn't want to say anything because you don't like being the smartest kid in your math group, and it's easier to just sit quietly and not say anything sometimes. So instead, you let somebody put up their hand and the teacher comes over and you say, hey, Mr. Guyage, we don't get it. And Mr. Guyage says, well, do you read the question? Yeah. Well, read it again. One of you read it out loud. And somebody says, okay, I'll read it out loud. Find the rate at which the balloon is going up. Oh, I know what we need to do. And it's like, oh, because you didn't actually read the question. You looked at the question and said, oh, it's something about a balloon. Anyone know what we're supposed to do? Agreed? Yeah. We've all been there, right? It's horrible. It's miserable. Guys, close reading. What do you know? What do you need to find out? And what kind of relationships do you have? What kind of relationships are there in the problem? On the previous one, what was relevant? Well, I've got an angle, I've got a triangle, I've got some rates of change. What's being asked? Oh, I need to know the rate of change of one of the sides of the triangle. What kind of relationships do I have? Oh my gosh, that's a right triangle. By close reading the problem, I mean, I didn't give you the problem, but imagine that you were just handed that problem on a piece of paper. By close reading the problem, you now know what the relationships are and what you know and what you're trying to find out. And that is much more important and interesting than it sounds. You're probably all going, well, duh. Of course we would do that, Mr. Armberding. But the more complicated the problem gets, the harder it is to understand what that information is, what you were being presented, what you were being asked. And sometimes it requires you to read a problem once and say, don't really get what they're asking, and go back to the beginning and start again. And sometimes it requires you to break out a highlighter and say, you know what, I'm going to highlight everything that looks important. Because it's really easy to just sort of zip past stuff. But with that highlighter, which is how you were taught to do close reading, you guys never had Protzeller, right? Even seniors, he'd retired. Yeah. I know he used to make a huge, he'd have kids sitting there with their highlighters going through and highlighting all the important stuff in the paragraph, and then they would talk about it. So what do you do next? You've got all that information, however you've done it, whether you just read it and were like, oh, okay, I get that, or whether you highlighted it out, maybe you wrote it off to the side as you highlighted it. You got to it, you highlight it, and you wrote off like I did. I wrote theta equals pi over 4, d theta dt equals 0.14. As I went through, I wrote everything off to the side. Develop a mathematical model. You might have to do this in stages, but you have to have a mathematical model. And so the question is, well, what mathematical model do I have? My first mathematical model on my example was, well, I know I got a right triangle. And then my second step was, I've got an X, I've got a Y, I've got a theta. And my third step was, oh, look, tangent. Boom, I've got a mathematical model. I had to know right triangle. I had to label what I knew, and then I had to think about the relationship between all the things I've learned over the years. It's not always going to be easy. In fact, I can guarantee you that sometimes this is going to be the sticking point. Because theoretically, once you've got a mathematical model, it's just calculus. Just take the derivative. You may get it wrong. You may make mistakes on taking the derivative, but it's just taking the derivative. And we know how to do that. Just a matter of making sure you do it right. But developing that mathematical model is key to the problem. You may come up with a mathematical model that's completely useless. But when you go back and you look at what you know and what you want to know, you may say, well, wait. Like I could have done a completely different mathematical model. I could have done this. I know X, I know theta. Well, we were just talking about a problem that used that. Oh, okay, good. Cosine theta equals x over that distance. That's a constant, so the distance is x over cosine theta, which is x times secant theta. Oh, but wait. I don't know anything about that distance. Could I do something? Yes, I could probably figure out how to relate that distance in x by bringing in a y, but if I'm going to bring in a y, why not just start over again and do it with tangent? Sometimes you're going to go off on, different use of the word, a tangent, a related, now that wasn't intended to be a pun, but I just wanted you to recognize that I was using it differently. You're going to go off on a tangent, and you're going to get something that could be helpful, but there's a way better way to do it. And that's to go back and say, oh, don't care about that, but do care about this. Hey, let's use tangent. So now I got a mathematical model. Part of developing your mathematical model, and I'm going to write this in capital letters. You may be really, really good at visualizing cones and spheres and hyperbolas and ellipses and whatever other weird shapes. Or you may not be. But if you draw a picture of the exact problem, it's a lot easier to look at and go, oh, wait, hey, look, I've got a right triangle there. Or, hey, look, I've got a rectangle or a square. Example off the quiz, which wasn't a related rates problem, but remember this problem off the quiz? Yeah. If you didn't have a picture, not very many people could just be told there are two intersecting parabolas with a rectangle in it. Now draw an equation relating the area of that rectangle. But if you draw a picture, all of a sudden this becomes easy. Oh, look, boom, area is that times that. Make sense? This is listed as a separate step. I feel like a mathematical model by definition is equations.
What is it? What's the difference supposed to be?
I don't know. I don't know. Possibly this is draw a picture and then think about the relationships, which then leads you to, in your mind, hey, I think I've got an equation that will work, and now you write down your equations that will work. I don't know. So don't worry too much about it. All right. Not all these steps are going to make perfect sense in the context of a problem. But just when we set it out, and maybe what we could do is this. When we say let's write the equations that relate data from part one.
See, that seems like a helpful step now.
Yeah. So we've come up with maybe 3 or 4 different equations that all have to do with our mathematical model. And then we go back and we analyze them and we say, okay, well, which of all these equations, which of this mathematical model I've developed includes all of this stuff? Good, let's start with those. All right. Differentiate with respect to time. You guys all know the abbreviation WRT.
Now I do.
I'm always stunned that the Twitter generation doesn't know abbreviations. It's like, wait, you guys abbreviate everything. How do you not know that one? Okay, never mind. Differentiate with respect to time. Guys, I'm going to write number 5, and then I'm going to talk about both of them because this is a sticking point. It is very, very important that you do number 4 and then number 5. And I gave you the example yesterday, and I'll give you another example from the balloon problem. We agreed that y was equal to x times the tangent of theta. We know that x equals 500 and theta equals pi over 4, which means that y equals 500 times the tangent of pi over 4, which is equal to 500. Okay, but I need to know the rate of change of y with respect to time. Oh, that's a constant, so that's 0.
Wow, more now.
You see the problem? I substituted in a value that is changing. So when I got down to the final end of the problem, everything was a constant, and the derivative of a constant is 0, which means that I got the wrong answer because I substituted too soon. It was okay to substitute 500 because I knew that wasn't changing. I would generally recommend that you just not substitute anything until the end. But here's what I don't like about not substituting the 500. And now I have to think about what do I do with x when the time comes. And because it's a constant, I don't have to differentiate it. So it still doesn't actually change it. But it's one more thing that I have to think about, that I have to worry about. What the heck do I do with this? X is constant. I'm okay with first substitute constants. I hate writing the word substitute. There are too many T's all separated by one vowel, but I think that's right. S-U-B-S-T-I-T-U-T. Okay, first substitute constants, but not things that are changing.
Guys, this is another reason why drawing a picture is helpful. You can easily tell what constant is.
Exactly. Exactly. Yeah, if you remember when I drew my triangle in a mirror, I wrote did I need to write d theta dt here? Did I need to write dy dt here? No. But the reason I do it that way is because now I see that this is changing and that's changing, and I can see that that's not changing. Because if that was changing, I would have wrote the x dt next to it. I put those things on the diagram because then I can see, oh, look, that's constant. That's not changing. It's not moving. So I don't have to worry about that one. I can plug that 500 back in, and now I can take the derivative with all the things that are changing. So this is big. Like I say, this is big, and it is a common mistake to substitute too soon and then not have a derivative. There's no derivative left to take. And finally, and I said this before, well, I said all these things before, interpret the solution. When you are interpreting a solution, you need to answer the questions what and when And what were the units? When the angle is pi over 4, the balloon is rising at 140 feet per second. You've covered the whole thing. By the way, do I want to say the height of the balloon is changing at 140 feet per second? Instead of rising?
So it could be going down.
Could be going down. Be specific. Sometimes it can be really, really annoying. Wow, I just finished this huge complicated problem and now I have to write a book. But hey, you know what? Real life, every project is going to have a cover page that lays out the conclusion specifically. And you write that cover page when you're done with the project after you've done all the work. And without the cover page, what you're saying is, hey boss, here's my 180-page report. Well, what's the conclusion? It's in there. Have fun. Well, he doesn't want to read the 180-page report. He wants to know the conclusion. Because if he trusts you, he's going to go spend money. And if you read the 180-page report, he probably wouldn't understand half of it anyway. I told you. He had money and he's a business major. He hired you for a reason. So as you walk your way through these problems, and I'll have this when I do the video, well, of course, there's going to be this video. I might even have a little handout that I can print out for you and I'll give you tomorrow. But as you walk your way through these problems, think to yourself, okay, did I do that? Did I do this? Did I do this? Especially if you're stuck. All the time, really. But especially if you're stuck. I don't know where to go next. Well, what have I done? Maybe I should go back and do one more close reading. Oh, because I didn't close read. I looked at it and said, oh, I know how to do this one. And then I got stuck. I skipped that step. I'll go back and close. Oh, look, there's a piece of information I completely overlooked. Didn't think about it. And it can be helpful, very, very helpful, which is why we have steps to look at a problem in this perspective. Now, as you get better, the steps will become instinctive. You'll just do them. And if somebody said, did you do the 6 steps? You'd be like, I don't know. I mean, I read the problem and then I wrote down some equations and then I differentiated and then I substituted. Oh, I guess I did do the steps. But you won't consciously think. Sort of like driving, right? You guys remember the first time you drove a car?
Yeah, it wasn't very long.
And you had to think, okay, I am coming up to a stop sign. I must take my foot off the gas and push the brake.
Yeah, I mean,
Oh, gently push the brake. Okay, what am I doing now? Oh, wait, no, I want to turn right. What do I do when I need to turn? Oh, I push the turn signal stalk upwards to its in signal right. Well, meanwhile, all of you behind you are going, get out of the way! We're trying to get somewhere while you're going through the steps in your mind. Well, after you've been driving for a while, you just don't even think about it. Did I signal? Well, of course I signaled because I always signal. So I must have signaled. I have no recollection of signaling because you didn't have to think to yourself, I am going to turn right and therefore I must push up on that lever. Just becomes instinctive. All right? Questions about the strategies? Okay, I'm going to erase. Last chance. Boom. It's as though they never existed. All right. I'm going to do these anyway. I sort of talked about these yesterday, but we talked about a sphere. Volume equals 4/3 pi r cubed. You generally in calculus, you'll be given these You won't be required to memorize what's the volume of all these various shapes. You get to know them eventually. You also start to see relationships. For example, do you guys know the volume of a cone?
1/3 of a cylinder.
Yeah, exactly. So now you know that this one is, what was it? Yeah, pi r squared h. And that's 1/3 of the cylinder. And then for this one, it's just 4 of these, except there's only one measurement. There's an R and no H. So, okay. Weird how they all just really relate to each other. You wouldn't think they would because they're completely different shapes, but they're all based on the same principles. What else do we know? Well, sometimes surface area can be useful depending on the question. Oh shoot, I knew surface area.
No idea what that is.
Well, we know it's squared. 4 pi r squared.
I feel like it's a derivative.
That does look like the derivative of volume, doesn't it? Interesting. Too bad we didn't get to that. Surface area of a cone. It's a little more difficult, actually, and I don't know this one at all. And if it's a derivative, then we'd have to do all sorts of weird stuff. Surface area of this one, 2 pi r squared is the top and the bottom, plus 2 pi rh is the circumference times the height for the sides. Remember unwrapping a cylinder and you get a rectangle? And so the top of the rectangle is the circumference of the circle times the height of the rectangle. Again, you'll be given these for the purposes of introductory calculus. It's not a terrible idea to just sort of start to put in the back. When you see formulas, just stick them in the back of your mind. It's like Pythagorean theorem. You know, you guys all know the Pythagorean theorem. Do you want to have to go look up the Pythagorean theorem every time you need it? No. Could you go look up the Pythagorean theorem every time you needed it? Yes, but it would get tedious. I'm not talking about, you know, taking a math test. Taking a math test isn't real life. But, you know, when you're trying to actually do stuff. So you got relationships there. So when we look at this, for example, what's that? Well, 4/3 pi is a constant. Guys, remember pi is a constant.
Yeah.
People forget that all the time. I've seen that on tests in this class.
Yep.
Treating pi as a variable. And then the derivative of r cubed, 3r squared times the chain rule. It's changing. And we could do the same thing with all of these. E plus 2, oh, see, now this gets fun. What if they're both changing? Product rule, right?
Yeah, super fun.
So 2 pi product rule says r dh dt plus h dr dt. Oh, well, that wasn't too bad. So this one, 2 pi times 2r dr dt plus all that.
When you say like the RDT, it sounds like you're just like making up words.
I love making up words, especially with like algebra and geometry classes. I just make up a word and they just assume that they just had forgotten the word, but they should have known it. And so then it throws them. And I always do it. I do it in such circumstances where they know what it means because it's in context. But then you can see them sitting there looking confused for a while. That's fun. Let's look at another common example. Yeah, we've got about 20 something minutes left. And then I'll have, you know, I'll give you guys a couple problems to take away out of the book. You guys ever use Slater.com? Any of you use that?
Yeah.
Good. It's an awesome resource. I've actually contributed, I don't know, a dozen or so solutions. I had one I contributed where they wrote the solution using something that you didn't learn until 2 chapters later. Well, that's fine, but you're the whole point of this is you're using this book. So don't tell people how to solve a problem using something they're not going to learn for another month and a half. It's like, so I submitted that one and just said, well, that's not really a great way to explain it. All right. A police cruiser is approaching a right angle intersection. And I'm going to write out this whole problem, which is tedious and boring, but I want us to do some close reading. From the north at 60 miles per hour, chasing a speeder who is headed headed east. The speeder is 0.8 miles from the intersection. Gosh, this is boring. And the officer is 0.6 miles north of the intersection. How fast is the distance between them changing? Darn it. The distance between them is changing. I don't have the problem all written down here, so I'm recreating this.
Oh, I see.
Them is increasing at 20 miles per hour. How fast is the speeder going? Now my arm's tired. All right, let's close read. I got a triangle here, right? Which direction's police cruiser going? South. With a rate of change. Going that way. Okay, length of the base of the triangle. Length of the height of the triangle. Hypotenuse of the triangle. Rate of change of the hypotenuse. Rate of change of the speeder. Step 1. 1, 2, 3, 4, 5, 6, 7, 8 pieces of information and 1 question. Guys, by doing this, I've narrowed this down and I've figured out everything that we know. We might not use it all, Although in a basic introductory problem, we're probably going to use it all because they wouldn't give us information we weren't going to use. Now, step 2 is develop a mathematical model. Well, first off, I'm told right-angled intersection, and I'm told north, and I'm told east. I am told you want to be careful here because of the direction that I'm going. And I'm told that, and I'm told that. That's everything I know. So step 3, making sure I read these correctly, write an equation relating all this stuff. Well, what's the equation that relates x, y, and b? Pythagorean theorem, agreed? D squared is equal to x squared plus y squared. Is anything constant?
Right angle?
Yeah, which means that there are no constants. There's nothing I want to substitute to make life easier at this point. Because this is changing, that's changing, and this is changing. So let's take the derivative. 2 times the distance between them times the rate of change of the distance between them is equal to 2 times the distance of the speeder from the intersection times the rate of change of the speeder plus 2 times the distance of the police officer times the rate of change of the police officer. And there's 2 things I don't know. I don't know dx dt, but that's what I'm trying to find. And I don't know d. But I can calculate d at that moment. D squared is equal to 0.6 squared plus 0.8 squared. You guys ready to do some mental math? What's 6 squared?
36.
So what's 0.6 squared?
26.
What's 8 squared?
0.64.
So what's 0.8 squared? See, you answered the wrong question.
I know it.
What's 36 plus 64?
100.
So what's 0.36 plus 0.64?
1. I can do that kind. I can't do like bigger numbers.
But all we did was times tables, right?
Yep.
But again, what makes it convenient to do in your head? So I'm going to divide everything by 2 just to make life easier. D is 1. The ddt is 20. X is 0.8. Dx dt is unknown. Y is 0.6. Dy dt is negative 60. 0.6 times 60. 6 times 6.
36.
20 is equal to 0.8 dx dt plus 36 minus 36. $56 is equal to 0.8 dx dt. 56 divided by 8. 7. 56 divided by 0.8.
70.
Step 6. at the indicated time, a speeder is traveling east at 70 miles per hour. Notice the context in my answer. At this time. Don't tell me anything about what he's doing before or what he'll be doing later. Because the only legitimate calculation we've done is when he's 0.8 miles and when the police officer is 0.6 miles. And when the police officer is going 60 miles an hour. I also said what direction he was going. Again, important bits. Important to know. Is the police officer ever going to catch him?
He speeds up.
Yeah, exactly.
Well, it's not a car just trying to get away from the police is only on the second.
Maybe he doesn't know the police officer's there, so he's not actually trying to get away.
What's busy roads?
The police officer was driving along, said, that guy looks like he's speeding. Pointed his radar gun directly at him, discovered that, hey, look, there's the information. This is actually how usually they got charts and tables. You know how they fly the planes around? They don't do it around here. But someplace, like in California, they'll have a plane that'll fly along. They've got little charts that'll tell you how fast somebody's going. And they'll use average speeds. They use that rate of, remember the, which one was it? Mean value theorem. That if you were here and then you end up there, at some point you have to be going the average speed. So they'll do a quick calculation. They got a chart that says if you got from here to here, and if you made it in less than a certain amount of time, well, then you must have been speeding at some point. We don't know when. Maybe you were speeding when you got there and then you slowed down, or maybe you were going slow and then sped up, but you couldn't have made it from here to here without speeding. And then they got a guy down the road who just flags down the red car. I got pulled over on my motorcycle one time. I had a sport bike, Honda Hurricane. Awesome bike, man. You freaking do wheelies on that thing. I did it by accident. Did that thing go by that?
No.
So I was in Rhode Island. I'd owned it for about 3 months. And I was sitting in an intersection and revved it up, redlined at 12,000 RPM. And I had it up, the light was about to turn and I wound it up to about 9,000 because I was going to go pretty quick. I wasn't going to speed. I had no intentions of doing anything illegal, but I wanted to go. And the light turned green and I started to let my hand off the clutch and my hand slipped and came off the clutch at 9,000 RPM. And that front wheel went about this high in the air and I went through the intersection on the back wheel. And it came down and I rode off. I was just like, at first it was just like, a massive adrenaline rush. And then I realized that, oh my gosh, that was so fun. And I went out in the country, in the middle of nowhere, and I found an empty road in the middle of nowhere, and I spent 45 minutes practicing popping wheelies on my bike. Oh my gosh, that was fun. What was my point? Where was I going with that?
The speeding is fun.
Well, no, I wasn't speeding. I never sped.
You got pulled over.
I never exceeded oh yes, I got pulled over because I was stuck behind this big RV. We were going up highway, I want to say highway 2, going over to Leavenworth. And I was stuck behind this big RV going like 45 miles an hour with a 60-mile-an-hour zone. It was really annoying. There was about 6 cars, including a sheriff. And we came to a passing lane, and I just immediately popped around, went up to like 80, which you're allowed to do, pulled in front of the RV, slowed down to 60, and off up the road I went. Maybe 61, 62, but who doesn't? And they don't care. 30 miles up the road, maybe less, maybe 5 miles up the road, there's another sheriff standing there, and he waves me over. And I pull over, and I see your driver's license, please. And I was like, well, what was I doing? And he says, well, I got a call from a police car back there. It said, it looked like you were going pretty fast. Or it looked like you were in a big hurry. And I said, oh, come on, look at my bike. It looks like it's in a hurry just sitting there. I said, I never exceeded the speed limit. And he kept me there for like 10 minutes and then let me go. And I was just I was ticked.
And then you really were in a hurry.
Well, I didn't need to be anywhere. I was out for a ride, but it was a complete abuse of power. I mean, he had no reason to pull me over. He had no evidence that I'd been speeding. And he's just like, oh, well, I'll harass the guy on the bike because he might speed. It's like, ugh. Yeah, it was annoying.
Discrimination.
Yeah, mostly just annoying. Here's the practice problems I'd like you to do. Should I erase this one or shall I leave it?
Oh, you can erase it. It makes sense.
Okay.
You've erased more important things today.
I prefer teaching off Blackboard or the whiteboard. Also, sometimes I miss being able to flip back through my notes and throw something I wrote earlier up onto the screen. But I actually like moving and talking while I write. I don't like sitting in a chair and writing. Why don't you do 2, 11, and 13? Those three should give you a pretty decent idea, get you in a comfort zone of, okay, I get the process. These are just process questions. Relate these things, solve a fairly straightforward problem. And I've got one more example. I've only got one more example to go over with you guys. I'm not going to do it today because I don't have time in 5 minutes. I think what I'll do is tomorrow I'll just go over the one example. In the meanwhile, I'm going to have this whole thing turned into a video, and then I'll let you work on the problems tomorrow. After I've done the one example, I'll let you work on homework. And then I think what I'll do is Wednesday, I'll let you work on homework some more, or maybe we'll split it up and maybe we'll do some together Wednesday and, wait, that's tomorrow, right?
Yeah,
Thursday and Friday. Because I do have that sort of packet that walks us through these steps. And guys, I would strongly recommend that you think about those steps as you're getting through this. Related rates really is something that gives people fits. And the problem is, thing one, trying to figure out what equation includes all of the stuff that you have or need. And thing two, taking more complicated chain rule derivatives. And so I would recommend that for now, you really think about those 5 steps. Use this process that I did, where you list the information, where you draw a diagram and then you write down all of your rates of change and values, and write them down with the variables. Don't just write 0.8, 0.6, 1, negative 60, 20, because to me it really helps to see that, oh look, there's a rate of change and a value. There's a rate of change and a value. There's a value looking for a rate of change. To me, it's super helpful to clarify in my mind, oh, I need an equation that has these things, because it's not just a bunch of numbers, it's variables and rates of change. And then as you're working your way through the problem, you could be thinking, okay, why don't I have a rate of change? Why didn't I use that? Did I not use it because I didn't need it? Or did I not use it because, oops, I took the derivative wrong? And that can be a really valuable tool for making sure you did it right. Because if you have to stop and think to yourself, okay, hang on a second. I know the derivative of d squared is 2d. Did I need that? Oh, shoot, I forgot to do the chain rule. And boom, you've caught yourself in a mistake. Okay. All right. Guys, that's it. I know. That's why I didn't start another story. I don't want my stories to be rushed.
Yeah.
Plus, you have to have time to go off on tangents.
Yeah. All storage and well, thank you.
Hey, you betcha.
Yes, how long is the 5.5 quiz gonna be up?
How long is it going to be up?
Yeah.
I don't think I put a time on it. I think I just loaded it.
Right, sounds good.
But it would be helpful if you got it done as quickly as possible because as we discovered on the last one, when I forgot to tell you, well, then I was waiting like a week and a half before I could even grade it and give it back to you. So,
when is 5.6 going to be due? It's not going to be this Thursday, is it?
no. 5.6, I think I've got it set up to be due Monday.
Okay.
I think put it in wrong. Instead of Tuesday, yesterday.
It's not, it's out of Google Classroom now. I checked this morning.
Well, yeah, because it's now when it's.
What?
Oh.
Okay. Well, I'm going to close the stream and then I'm going to go look at Google Classroom.